Tangam, welcome to Gully Classroom. This is the third lecture on the chapter Atoms in CBSE 12th Standard Physics Chapter 12 Atoms. This is the third lecture taken in English. This is the third lecture taken in English. Okay. Before we get into the core of this lecture, before we get into the subject matter of this third lecture, which is Bohr's model of an atom, postulates of Bohr, Bohr's quantization rule. Let us do a very short recollection of the limitations of Rutherford's atomic model, because whatever are the limitations of Rutherford's atomic model is improved in Bohr's model. So we need to understand the limitations of Rutherford's atomic model. Here, according to Rutherford's atomic model, at the center there is a nucleus, an electron is going around the nucleus. The electron is a charged particle and also it is changing its velocity at each and every position. This electron is changing its velocity vector in each and every position. Because the direction of velocity is changing, this electron is an accelerated particle. If velocity is changing, electron is obviously an accelerated particle. It is a charged particle. According to Maxwell, an accelerated charged particle simply radiates energy, and if the electron is radiating and losing energy, it will be pulled towards the nucleus. The nucleus will be pulling the electron, and as long as the electron has enough energy, it will be simply going around the nucleus. But as it loses its energy, according to Maxwell, an accelerated charged particle radiates and loses energy. This particular electron will slowly lose its energy and spiral into the nucleus. This particular electron will slowly lose its energy and spiral into the nucleus. And here the electron will collapse into the nucleus. The atom will become unstable. Sir, but all of us are very stable. I am made up of atoms. I am stable. You are made up of atoms. You are stable. So, Rutherford must be doing some mistake in this explanation. Okay, let me ask you something. Is Maxwell absolutely right? Yes, here Maxwell is absolutely right. Maxwell's theory has been proved mathematically. Maxwell's theory has been proved mathematically. So, Rutherford was not able to accommodate Maxwell's idea. Rutherford was not able to explain the stability of the atom, even though Maxwell is suggesting all atoms according to Rutherford will become unstable. Are you able to understand this? Okay, so Rutherford was not able to explain the stability of the atom. What is the second limitation, sir? Rutherford was not able to explain the discrete spectrum of the atom. According to Rutherford, an accelerated electron must be radiating and absorbing all wavelengths. So the atom must be absorbing and radiating all wavelengths. But when they are doing a lot of experiments, they are observing that the atom is absorbing and radiating only specific wavelengths. I am repeating the idea once more. According to Rutherford, what he is assuming? He is assuming that the atom will absorb and radiate all wavelengths, all lambda values. But when they are doing experiment with H2 gas, hydrogen gas is absorbing and radiating only specific wavelengths. Rutherford was not able to explain why discrete spectrum of atom is happening and not continuous spectrum of atom is happening. Okay, so sir, I am not able to understand this particular point clearly. That is okay. This particular point will only be clearly understood after studying Bohr's model of an atom. So when we are studying Bohr's model of an atom at a particular point, I will recall this second point and explain to you why Rutherford was not able to explain discrete spectrum of an atom. Okay, sir. What is the meaning of the word discrete? A rough meaning of the word discrete is specific. Let me repeat myself. A rough meaning of the word discrete is specific. Remember this, Rutherford was not able to explain discrete spectrum of the atom because according to Rutherford, an accelerated electron which is present in the atom must absorb and emit, radiate all wavelengths, but experimentally only specific wavelengths are absorbed and radiated. Okay, now let us go for Bohr's model of an atom. After the limitations of Rutherford's model of an atom became very obvious. After the limitations of Rutherford's model of an atom became very obvious, what is happening? They are Bohr in the year 1913 is introducing his own idea and giving some postulates as Bohr's postulates. Let us try to understand Bohr's postulates. According to Bohr's postulates, nucleus is the center of the atom. So let us have a positively charged nucleus here. The electrons are revolving around the nucleus in specific orbits. So let me draw specific orbits over here. First orbit, second orbit, this is the third orbit. What about the fourth orbit, sir? This is the fourth orbit. Right. So let me give these particular orbits certain names. What are the names? Let me call this L shell, let me call this L shell, and let me call this M and N. This is going to be called as ground state. Okay, sir. What about L? We will call this excited, EXCAT. Okay, I think I am excited spelling. Okay. EXCAT, excited state 1. L is excited state 1. M is excited state 2. N is excited state 3. Okay, sir. What else can we write? Here, let me call the N value as 1. Here, let me call the N value as 2. Here, let me call the N value as 3. Here, let me call the N value as 4. As we go on, I will give a better explanation of the N value. Just to hold on and follow along with me. What about the energy, sir? We will call the energy level of this particular. Let us write the energy level in red. Just to for understanding sake. This is the energy level 1. Here I am going to write energy level 2. Here I am going to write energy level 3. Here I am going to write energy level 4. The energy level 1, as it is very close to the nucleus, will be controlled more by the nucleus. Hence it will have less energy. The energy level 2 is slightly away from the nucleus. When compared to energy level 1, energy level 2 is slightly away from the nucleus. And energy level 2 will have more energy because as you go away from the nucleus, you are getting out of control of the nucleus, and since the nucleus is not able to control you, as you go away from the nucleus, your energy level will increase. Are you able to understand this particular idea? So the more nearer you are to the nucleus, the lesser you will have energy. The more away from the nucleus, you will have more energy. Okay, sir. Now, what is the explanation here? The electrons revolve only in specific orbits, which are called as stationary orbits. What are stationary orbits? The electrons are rotating in these specific orbits, K, L, M, N. With respect to K, when the electron is revolving, each and every electron in K will have the same radius, energy and angular momentum. Each and every electron in K orbit will have the same radius, energy and momentum. They will be constant. So it is called as stationary orbit. Because radius, energy and angular momentum of any electron in that particular orbit L is always constant. In that particular orbit L is always constant, or in that particular orbit M is always constant, or in that particular orbit N is always constant. Each and every shell is called as stationary orbits. Okay sir, I am understanding the idea of radius and energy. What about the idea of angular momentum? Kindly recall it for a couple of seconds. What is angular momentum? Okay, let me do this. Let us have a positively charged nucleus here. Let me assume an electron which is rotating here. Okay, so let us say the electron is going like this. This is the velocity vector. Okay, let me put the momentum, not the velocity vector. This is the momentum of the electron. This is the momentum of the electron. Okay, here I am going to draw the r vector or position vector of the electron. R vector and position vector of the electron. Here, this can be considered as the radius. P vector can be considered as a tangent. The angle between them is 90 degrees. Angular momentum means turning effect. Imagine pulling a door. It is turning like this. Am I right or wrong? Imagine pulling a door. It is turning like this. That turning effect is called as momentum, angular momentum. What is the formula for angular momentum or L vector? It is simply called as R vector cross P vector. So you are going to do cross product of R vector and P vector. So the formula is RP sin 90, because the angle between them is sin 90. How are we going to do this, sir? Give us a better idea. Slide this particular R vector over here. While doing vector cross multiplication, you can slide this particular vector over here. So here I am crossing P vector and R vector. Here also the angle is going to be 90 degrees. So I am substituting sin 90 over here. Sin 90 value is obviously 1. So I will have R into P. What is the value of P? P is momentum. Momentum formula is mass into velocity. So angular momentum can be written as mvr. Angular momentum can be written as mvr. So since angular momentum is a cross product, it must have a direction. Am I right or wrong? You are obviously right. So what is the direction of angular momentum in this particular situation? How are you going to do this? R cross P. Take your right hand, orient your fingers in R vector direction. Orient your fingers in R vector direction. Curl the fingers towards P vector. Curl the fingers towards P vector. The thumb is coming out of the board, which means the thumb is coming out of the board, which means this is the direction of L vector, angular momentum. This is the direction of angular momentum. If a vector is coming out of the board, you will put a dot to indicate it. If a vector is going inside the board, you will put a cross to indicate it. Sir, what is the idea behind this? Imagine an arrow coming towards you. If an arrow is coming towards you, you will only be able to see a dot. So a vector coming out of the paper is simply represented by a dot. Okay, now imagine an arrow which is moving away from you. Imagine an arrow which is moving away from you. What will you be able to see? You will be able to see only the bush of the arrow, the feathers behind the arrow. That is indicated with the cross. So when a vector is growing inside the board, when a vector is going inside the board, you are representing it by using a cross. Are you able to understand the idea of angular momentum? So each and every shell, K shell, L shell, M shell, N shell, will have a constant radius, constant energy and constant angular momentum. Okay sir, what is the speciality of these specific orbits? Bohr is giving a special idea with respect to these orbits. Okay sir, what is the speciality? What was the first limitation of Rutherford? Rutherford according to Maxwell, the first limitation of Rutherford, according to Maxwell, an accelerated charged particle will radiate and lose energy. It will spiral. The electron will spiral and collapse into the nucleus. Atom is not stable. Okay, now here Bohr is doing an assumption. Here Bohr is doing an assumption. What kind of assumption? When the electron is moving in these particular what orbits? Stationary orbits. They do not emit any radiation. When the electron is revolving in these particular K shell, L shell, M shell, N shell, they do not emit any radiation. This particular type of revolution is called as stationary revolution. This particular type of orbit is called as stationary orbit. So here the electron is not losing any energy. The electron will not collapse into the nucleus. That is the argument of Bohr. That is the argument of Bohr. Okay, sir. What is the condition with which each and every stable orbit was defined by Bohr? Bohr is giving some ideas on how to define these particular stable orbits. Let us look at them. Bohr is defining each and every stable orbit with respect to the angular momentum of the electron in those orbits. With respect to the angular momentum of the electron in those orbits. Okay, let me give you an idea. For n equal to 1, what is the angular momentum? The angular momentum can be written as 1 into h divided by 2 pi. What about for n equal to 2, sir? The angular momentum can be written as 2 into h divided by 2 pi. What about n equal to 3, sir? The angular momentum can be written as 3 into h divided by 2 pi. N equal to 4. What about the angular momentum, sir? It can be written as 4 into h divided by 2 pi. So for each and every shell, Bohr is defining with respect to angular momentum. Okay, here can I generalize this idea like this? What is the formula for angular momentum? Sir, just before a couple of seconds you taught us. It is mvr. So mvr can be written as n into h by 2 pi, where n is an integer. N can be 1, 2, 3, 4, dot, 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 dot. Okay, so n cannot be a fraction. The orbits have to be these specific orbits. N cannot be in between these orbits. There cannot be electrons moving here. In order to indicate that particular idea, n is always an integer. So n can be 1, 2, 3, 4 and such values. It cannot be, n cannot be 1.5, n cannot be 2.5. That will indicate orbits in between these stationary orbits, which is not possible according to Bohr. Which is not possible according to Bohr. So this is how Bohr is defining the angular momentum of these stationary orbits. Bohr is defining the angular momentum of these particular orbits. Okay, sir. The next idea is, here you are defining everything with a particular constant value, which is h divided by 2 pi. What is the value of h, sir? What is the value of h? Kindly give an idea about the value of h. Okay, Gana. Here h is called as Planck's constant. 6.626 into 10 to the power of minus 34. H is called as Planck's constant. When you are studying the unit light, we will study that light has dual nature. Light can behave as a wave and light can also behave as a particle. Light has wave nature and also particle nature. Okay, sir. So if light can behave like a particle, what is a single light particle called as? A single light particle, a single packet of energy with respect to light. A single packet of energy with respect to light is called as photon. Is called as photon. What is the energy of this photon? E is equal to h nu. Sir, what is nu? Here, this particular symbol is called as nu. and it represents frequency. If you are not comfortable with nu, you can also write E is equal to HF. So what is the formula for frequency? Frequency is nothing but C by lambda. So the energy, each and every single packet of energy is called as E is equal to hc by lambda, where h is the Planck's constant. Okay, Gana. Now let us look at this. Bohr's definition of stable orbital, Bohr's quantization principle. The angular momentum of the electron about the nucleus in each and every stationary orbit is quantized. So what is the meaning of quantized? Quantized means specific. Discrete is also specific. The rough meaning of discrete and quantized are one and the same. They simply mean specific. So the angular momentum is quantized and it is always an integral multiples of h by 2 pi. How, sir? For the first shell, what is the angular momentum? We can simply write it as 1h by 2 pi. For the second, we can write it as 2h by 2 pi. For the third, we can write it as 3h by 2 pi. For the fourth, we can simply write it as 4h by 2 pi. So it is in complete multiples of h by 2 pi. So we have already seen what is the value of h. H means Planck's constant. So y is the unit of Planck's constant given as joule second. Okay, let us do this. Look here, E is equal to h nu. What is the unit of nu or frequency? 1 by second. We are going to find the unit of h. So let us simply put h here. Energy is written in joules. If we bring this particular s here, joule second is equal to h. So the unit of h or Planck's constant is joule second. The angular momentum is in integral multiples of h by 2 pi. That's basically the idea. Okay, sir. Now let us go for the next point. Here, let us say I want to represent these particular shells here. Let me represent these particular shells here. 1, 2, 3, 4. This shell I am going to call K over here. N equal to 1 or K shell. Can I write it like this? Okay, N equal to 2. Or I am going to write it as L shell. Here I am going to go for N equal to 3 or I am going KL M shell. Here I am going to go for N equal to 4 or N shell. Let us say an electron is present in N equal to 2. Right now it is decaying to N equal to 1. What will happen, sir? This electron will decay from N equal to 2 to N equal to 1. Just for understanding, I am going to work over here. N equal to 2 to N equal to 1. An electron will decay from this point to this particular point. An electron will decay from this point to this particular point by releasing a photon, by releasing a packet of energy. What will be the energy, sir? It will be the difference between these two energy levels. Let me indicate the energy levels using red. Here the energy level is E1. Here the energy level is E2. Here the energy level is E3. Here the energy level is E4. The energy level as we move away from the nucleus, the energy level will increase. As we move away from the nucleus, the energy level will increase. K is very near to the nucleus. It has less energy. So as we move away from the nucleus, the energy level will increase. When this electron is decaying, it will release an energy. E2 minus E1 is equal to Hc divided by lambda. Just before a couple of seconds, I told you how to define the energy of a photon. So Hc by lambda is the way to define the energy of the photon. So what is the energy of the photon released when an electron is decaying from n equal to 2 to n equal to 1? It is nothing but E2 minus E1. E2 minus E1. The difference in the energy levels is simply released as photons. The idea is this. Let us say each and every point. If a rich person is becoming a poor person, he must lose some money. Am I right or wrong? If a rich person is becoming a poor person, he must lose some money. Here, the photon indicates the money lost by the electron when it is moving from a higher energy level to a lower energy level. Okay, sir. Let us say the electron comes here. What will happen? Let me repeat. What will happen if I am going to give the same energy to this particular electron once more right over here? This electron will get excited and go to the n equal to 2. This electron will get excited and go to n equal to 2. Okay, it will stay there for 10 to the power minus 7 seconds and simply decay. It will stay there for 10 to the power minus 7 seconds and simply decay once more and come down. It will simply decay once more and come down by releasing the same photon. E2 minus E1 is equal to Hc by lambda. Okay, are you able to understand this idea? Let me do a better illustration. Can I rub this off? I am going to do a better illustration of this idea so that you will understand this concept in a better way. Right. Okay. So this is n equal to 2. This is n equal to 1. Yeah. Okay. Let us say an electron is decaying from n equal to 4. Sir, can this electron come directly to this particular point n equal to 1? Yes, it can do this. What will be the energy of the photon released? The energy of the photon released will be E4 minus E1 is equal to Hc by lambda. Okay, sir. Let us say an electron is coming from this particular point to this particular point. What will be the energy released? E3 minus E1 is equal to Hc by lambda. Okay, sir. What about from here? From here, you can simply write E2 minus E1 is equal to Hc by lambda. Okay, if you kindly note over here, H is an constant. 6.626 into 10 to the power minus 34 joule second. C is a constant. Speed of light 3 into 10 power 8 meter per second. So lambda is the only variable. Because here the energy levels are different, each and every lambda will also be different and specific. As the energy levels are different, each and every lambda will also be different and specific to this particular decay. When an electron is moving from a higher energy level to lower energy level by releasing a photon. When an electron is moving from a higher energy level to a lower energy level by releasing a photon, it is called as decay. When an electron is absorbing a photon and jumping from a lower energy level to a higher energy level, it is called as excitation. When an electron is jumping from a lower energy level to a higher energy level, it is called as excitation. So, if you are going to give this particular photon to an electron here, it will once more jump here. If you are going to give this particular photon to an electron here, it will simply jump from this point to this point. If you give this particular energy to a electron here, it will simply jump from this point to this point. Now let us study here. When an electron makes a transition, what is a transition? Transition means movement. When an electron makes a movement from EH, a higher energy state or a higher energy level, to EL, a lower energy state, it radiates energy. What kind of energy is it radiating? It is radiating energy in photons, which is equal to the difference in energy levels, By absorbing the same energy, the electron can once more shift back to the higher energy level. Yeah, are you able to understand this particular idea? Yeah. let me give you a very small illustration of the way in which energy is quantized. Let me give you a very small illustration of, okay, let me do it over here. I don't want to rub this particular beautiful diagram. Isn't this beautiful? I am having so much fun. Okay, quantization. Quantization, just like I told you, what is the meaning of quantization? Quantization or discrete means specific values. Here, let us say this particular vertical value is h divided by 2 pi. Again, this particular vertical value is h divided by 2 pi. This particular value is h by 2 pi. This particular value is h by 2 pi. This particular value is h by 2 pi. Okay. Now, let us consider electron like a ball. The ball can rest either here or here or here or here. It can rest only in these specific energy levels. So, energy levels are angular momentums. Here, I can write the angular momentum as 1 h divided by 2 pi. If I am going to write the energy level here, if I am going to write the angular momentum here, I need to consider 2h by 2 pi. This is 1h by 2 pi, this is second h by 2 pi, so I am going to write 2h by 2 pi. Okay, this I am going to write 2h by 2 pi. Okay, sir. What about here? I am going to write 3h divided by 2 pi. What about here? I am going to write 4h divided by 2 pi. What about here? I am going to write 5h divided by 2 pi. Are you able to understand how the value of the electron, the value of the angular momentum of the electron is quantized, or will only take only specific values which are in integral multiples of h by 2 pi? Yeah? Cheers. I hope you guys understood this. Okay. This is more or less enough. But let me tell you a very small story. It is a fun story. So I am going to take the time to tell you that story. What is the story, sir? According to classical electromagnetic theory, let me repeat myself. According to classical electromagnetic theory, what is Maxwell telling? An accelerated charged particle will always lose energy. An accelerated charged particle will always lose energy. Okay, sir. Okay, sir. I am understanding that. That is 100% true thing. There are no doubts in it. Okay. Then how can Bohr suggested that there are specific orbits in the atom in which the electron is not going to release energy. There are specific orbits in the atom in which the electron is not going to release energy. How did Bohr come up with this idea? In this particular time, they were doing a lot of experiments. What kind of experiments? They were taking hydrogen gas like this, and they were simply sending light. Like this. What is the energy of light? E is equal to h nu, or E is equal to hc divided by lambda. Okay, what they are noticing is hydrogen is absorbing certain frequencies. What frequencies is hydrogen absorbing, sir? 6.3 nanometers. What is the next thing it is absorbing? 486.1 nanometers. Okay, sorry, 486.1 nanometers. The next thing is 434.1 nanometers. The next thing is 420.2 nanometers. These particular frequencies are absorbed by hydrogen. The scientists were not able to explain why these frequencies were, why these wavelengths. Nanometers means wavelengths. Why these wavelengths were absorbed? So what they did, they thought that there could be some kind of a mathematical relation between these specific wavelengths, and they published these values in the newspaper and challenged the general public to find the relation between them. Now, there was this amazing maths teacher. What did he do? This maths teacher, called as Balmer, found a relation between all these values. What is the relation that he found? He found that lambda is equal to 364.56 m square divided by m square minus 4, where m can be 3, 4, 5 and 6. So if you are substituting 3, 4, 5 and 6, you will get these particular values. you will get these particular discrete wavelengths. You will get these particular specific wavelengths. Sir, wait a second. Didn't I study this somewhere? Now recall the second limitation of Rutherford. Didn't Rutherford find it difficult to explain the discrete spectrum of atoms, or Rutherford was not able to explain why hydrogen is emitting and absorbing only specific wavelengths? But Bohr was able to explain why hydrogen was able to absorb and emit only specific wavelengths, because only specific electrons are decaying from specific energy levels. Only specific electrons are getting excited between specific energy levels, and because of this only specific wavelengths are being emitted. Didn't we study that particular point over here? Are you able to understand the entire thing? Yeah? Are you enjoying the lecture? Yeah, cheers. Okay, Gana. So, Bohr, what did he do? He took Rutherford's model. Let me repeat. Bohr took Rutherford's model and he took the Balmer's idea. What is the name of the mathematician who did this work? Balmer. He took Balmer's idea and integrated Balmer's idea into Rutherford's model. Bohr integrated Balmer's idea into Rutherford's model and developed Bohr's postulates. Okay, sir. What else can you talk about in this particular idea? Let us take a nucleus. Here, this is my first shell, second shell, third shell, fourth shell. Just for illustration purposes. Okay, so here I am going to write n equal to 1, n equal to 2, n equal to 3, n equal to 4. Here E1 is nearer to the nucleus. So E1 is lesser than, E2 is lesser than, E3 is lesser. Oh, greater than. I am sorry. E1 is, here. E1 is lesser than E2, which is lesser than E3, which is lesser than E4. Here, what is the next thing, sir? How are we going to write the angular momentum? 1h divided by 2 pi, 2h divided by 2 pi, 3h divided by 2 pi, 4h divided by 2 pi. Now let me ask you a question. What is the angular momentum of nth shell? What is the angular momentum? What is the angular momentum of shell n or nth shell according to Bohr's idea? Okay, let me do this. K, L, M, N. So nth shell means the angular momentum is 4h by 2 pi. Nth shell means the angular momentum is 4h by 2 pi. Also, which shell has the lowest angular momentum? Which shell always has the least energy, least angular momentum? The shell that is very near to the nucleus always has the least angular momentum. It always has the least energy. What about the valence shell? The valence shell, which is present as much away from the nucleus as possible, will always have the highest amount of energy and the highest amount of angular momentum. The valence shell will always have the highest amount of energy as well as the highest angular momentum. Yeah, that more or less closes this lecture. In the next lecture, we will continue studying about Bohr's model. We will do derivation on how to derive the radius of these particular orbits, and also we will derive the velocity of the electron in these particular orbits and do some bored problems based on them. And we will do some bored problems based on them. Hope you guys enjoyed this lecture. I enjoyed taking classes to you. Cheers and thank you. If you like our lectures, subscribe to our channel, recommend our channel to your friends. Like the videos, share the videos. Let us have fun learning physics together. Cheers and thank you. Cheers and thank you.